We are once again recording, and this will be the fourth module and the last pure Python module. So we've talked about a lot of data structures and control flows, and now we want to talk about object-oriented programming. And this is a lot of the quote-unquote special sauce that makes Python really usable. So if you've done like QBasic or something like that, you don't necessarily have access to some of these tools, and that's so I want to kind of illustrate what those are. So Python is an object-oriented programming language. As we've emphasized, Python supports many different kinds of data. We've got integers, floats, strings, lists, dictionaries. Each one of those objects has a type or a name, which I've just illustrated what they are. And then there's an internal data representation of that. So there's an internal format for that data. Having that internal format allows for a set of procedures or interactions that that object can do. So each object is an instance of a given type. So 1, 2, 3, 4 is an instance of an integer. It's a given integer, or an instance is the term that's used. Hello is an instance of a string. Each instance of a string has access to all of the methods associated with a string. So we've talked about some of these, mostly with lists. We've talked about sort and reverse as methods associated with lists. Every list that we've worked with is an instance of the type list, of the template. You can think of it as a template or something, but is an instance of the type list, and every instance of the type list has access to sort and reverse and a bunch of other methods that we haven't even gone into. You can create new objects of a given type, you can manipulate objects, and you can delete or destroy objects. So the important thing is that objects are a data abstraction that captures a given structure. It captures data as attributes in a given structure or internal representation, and it has an interface that allows us to interact with it in predefined ways. So again, the example that we've used a lot is for lists, we know how to sort them and reverse them. For strings, you can capitalize them or lowercase them. There's built-in methods for doing common things with these. And then we've also indexed them. We've done all this stuff. We've done all of these as examples. So here's all the possible lists, or not all of actually, but here's some of the possible ones that we've talked about. Append, extend, which can connect lists, or which can lengthen lists. Count, which can count through them. Index, which can identify the index number. Insert, which can add to a list based on a given index number. Pop, which removes and returns an object from a list, an item from a list. Remove just removes the item from the list, and then reverse rearranges them in a different order, and sort orders them alphabetically or numerically. There's many other built-in methods, and you can see those in the Python documentation, but these are the most common ones. The point isn't that you need to memorize them, but that whenever you see a dot and then a structure like this, you can know that that's a built-in method, and you can check Python documentation or check in the help section of Twedit to understand what's going on there. So far, we've worked with the built-in types in Python, lists, strings, dictionaries, etc. But we can actually create our own classes and create instances of those classes. So we kind of hinted at this when we were going through dictionaries and using examples of cells. Actually, we can create a class called cell that has attributes like volume, speed, division rate, receptor number, and things like that. And we can create many instances or versions of that class. And each one of those will have their own data, but they will all act in the same way. And that's really how CompuCell will help you simulate the system of your choice. one thing that gets involved in making, and I think you guys use this in the colon crypt model, and I think that's the only one you'll use this in. There's things called subclasses. So if you think of an animal, right? People, humans, cats, rabbits are all examples of animals, and students are examples of people. So if you had a Python object called animal, it might have a certain set of basic attributes: age, mass, temperature, core temperature, hunger level, etc., drowsiness, or whatever, to simulate what that animal is doing. And then specific subclasses of those might need additional characteristics. Like rabbit might need an additional characteristic for like fear, for how afraid it is because it's gonna like scatter or whatever. Or a cat might need the additional characteristic for how it will respond to catnip. Or a person might need additional characteristic for screen time or something like that. And so you can build out your parent class, and you can build out your child class, and the child class will inherit all of the data and behaviors of the parent class, and it can add more there. And then student might be a subclass of person. And then student would include maybe the characteristic of study time or some other methods like pay tuition or something that other members of the superclass or parent class don't need. So that's all kind of abstract. Let's look at a simple example. So we're going to use a class called coordinate which we're defining. And it's going to have, what goes in there is any parent class that's relevant and any attributes. Class is the keyword, which acts just like def for functions. So the same way that def identified functions, class is going to identify your user-defined classes. The word object here is not always necessary to indicate, but this is an example, indicates that coordinate is a Python object and inherits all of its attributes, and coordinate is a subclass of object, and object is a superclass of coordinate. You don't have to include this if you aren't specifically trying to inherit some of the characteristics of the superclass. So, and this will be more clear when we do an example in just a second. So what are attributes? Attributes are the data that belongs to the class. So we talked again about animals having, a heart rate, a mass, a location in time and space, a drowsiness level. Those are the data that are part of it. If we think about this coordinates example that we're about to do, a coordinate is just going to have two numbers. It's X and it's Y location. And then in addition to attributes, you have something called methods, which are things that object or that class does based on its attributes. So if we think about the example of an animal, based off of its drowsiness level, maybe once its drowsiness level hits 75 out of 100, it goes to sleep. So you could have a method called sleep, which would make it not move in XY location, et cetera, et cetera. For a coordinate, you might have a method that is based on defining the distance between that coordinate and some set point at any given time, calculating that out. So, okay, that's enough abstract. Let's go to, let's set one of these up. Oops. I want to do that, and I want to do that, and just open a new notebook. Mm, okay. Okay. So class, see how it's bolded in green? That indicates that it's a kind of a keyword in Python. You use the colon and then the indentation comes automatically. That's 2 underscores there. Let me make this clearer. Okay. We've created our first class. So keyword class, the name of the class, whatever it's inheriting, you can't, object is kind of a default one. You don't necessarily have to include that. And then you have what's called a dunder init. Dunder means double underscore. And it's a special method. Whenever you see a dunder in Python, it means it's a built-in method in Python. And it's set up that way so that you don't accidentally overwrite it. But basically, it's a dunder init is for initializing an object of a class. And it has an attribute, it has 3 attributes: self, which is automatic. That's where it's going to store, that's what's going to attach to the given items of or what each instance is going to attach its attributes to. And then the attributes you want to work with. In this case, for a coordinate, for a point on a coordinate system, we need an X attribute and a Y attribute. So these are input arguments. And then the X location is going to be the self.x location is going to be the how we store the variable, the value for X, and self.y location is going to be how we store the value for Y. I think it's best practice to have these attribute names be distinct from the input argument names, but it doesn't actually matter. So now when I run this, see it's run, I've created that class. Now, if I want to create an instance of that class, I do coordinate, and then I do that. You don't have to include self. So you say, or you can do X equals 3, Y equals 5 if you want to keep it identified for well identified for yourself, but you don't have to. So now I've created that object. If I want to access the attribute for that object, I do instance dot X location and instance Y location. Right? So instance 1, what is the type of instance 1? Remember, whenever you have something in Python, you don't know what it is, you type in C. It is a coordinate and it's attached to main, means it's inside this program that it comes from this program that we're running, and it is a coordinate in there. And then you can access those X and Y variables. Now, if it's just a matter of keeping track of those variables, you could do this with a dictionary, right? We haven't added any features that we didn't have with the dictionary. You could have just done coordinate 1 equals X location 3, Y location 5. So far, this is the same thing, right? So far, this has the same capability as this object we've created. But that's because we haven't added any special methods yet. So this is what we showed. Instance 1 equals coordinate 3, 5. Same thing as there. You can do origin. You can do right now. You have 2 instances. Now it is easier to enter it this way. Whereas if you had to write out the dictionary, you would have to write out all of that. But it's still not that special. It's still not that different. It actually doesn't get special or different or valuable until you include a method. So what exactly is a method? We've hinted at it. A method is a procedural attribute. It's a function that works only with that class. Python always passes the object as the first argument and self, that's what that self is for, and then use the dot notation to access any methods afterwards, any methods or attributes. So we used dot, right? Instance 1 dot y location to access the attribute there. We can do the same thing with the method we're about to create. So let's edit our class now. So we've done our constructor, our dunder init. Now let's add a special method. So self, again, is its own, it refers to itself. And other is some input argument that has to be added. I need to have my colon there so I indent properly. I'm just going to shorten this to loc because I want to save the screen real estate. Okay. And then just like a function, you often want to return. See, we're using the dot notation to access data, access attributes. Okay, so now I'm going to hit Shift Enter. Now I've updated classes to have this method called distance. Now I've got these 2 coordinates, right? Instance 1 at 3, 5 and origin at 0, 0. Let me add another cell here. So if I want to access the method for this, so how do I use the method? I call it the same way I call a function. So if I want to ask instance 1, how far are you away from origin? I do instance 1 dot distance. And then what are the input arguments for distance? Self. Well, self is taken care of automatically. So then I just have to enter in other. Well, other is origin. I didn't run this. Oh, I'm going to run this. Shift Enter. And I got to run this again because I have to see this is a 7 and that's a 10. I need to run this again so that the instance 1 is a coordinate that has access to distance and origin is a coordinate that has access to distance. Okay, so now this has been run and now we're not going to get an error, right? So what happened is it returned its distance from origin. I could similarly do origin, distance, instance 1. I misspelled it. Okay, sorry about that, guys. It's the same thing. And if I do origin, distance, origin, I get 0. Okay. Do we all follow what happened there? Are there questions? what are the conventions regarding capitalizing these terms? So classes are typically capitalized. Methods typically are not. I don't know that there's a specific convention around. In fact, I bet typically these are not capitalized. Typically it would be like this. But when you're doing large scale simulations, you actually don't end up naming your instances that much. You put instances like in a list or something and then do it all at once, which we'll show in a second. Okay. Other questions at this point? This is kind of the whole point of today, is what we're getting to. Okay. Let's talk about what self and other are doing.
I did want to, Bobby, jump in real quick.
Yeah.
I mentioned that the capitalization stuff, like Bobby was saying, is just a convention. It's not, it'll work even if it's not capitalized. You just have to make sure that your capitalization is consistent when you call those functions later. Right.
Yeah.
Yeah. I just wanted to point out that it's not, you do not have to capitalize your classes. It's just generally a convention that people use.
All right. And then the other thing is, if I do C here, it's not going to throw an error. But if I do 2, you see the color changed, right? All of a sudden this green and black means it doesn't work. So, yeah, so that's another way. When you see different weird color changes all of a sudden, that's when you know you're actually getting an error. So there's a question from Norma. Let's talk about self versus other. So during the definition stage, when you're defining a class, you have to include self as the first input argument to both the attributes up here and the methods down here. And you can have more than one method per class, but you can only have one constructor per class. Only one set of methods one set of attributes per class, but you can have as many methods as you want. But for both methods and attributes, the first input argument is self. It's basically designating the identity of each instance that's going to be created. And then we attach these methods, we attach these attributes, we attach the data to the self. Inside the coordinate, we have, inside the object definition, inside here, we access internal data via self. Outside of the definition, we're going to access data through dot notation based off of name, based off of the name of the object. So self gets replaced by the name of the object when you're outside in the global environment, right? Because inside here, there's only one object at a time, right? So it knows which one itself is. Outside here, it needs its name to be able to know which one you're talking about. What other is doing here is an input argument. There could be any number of input arguments. Like maybe the distance depends on maybe the distance depends on the wind parameters or something. Well, not in a biological simulation, but maybe there's some other factor that that matters here. So you can put any number. It's just like a function. This part here is just like a function. Any input argument, any outside data that you're going to need to enter here. In this case, distance is just one. It's just a calculation from self to some other point. So we need some other point. So you could say, other x coordinate and other y coordinate. And that way you don't have to specify, it doesn't have to be distance from another instance of coordinate. It could be a distance from any other point. But whatever these are, you're going to have to use out here, right? It's got to refer to these out here. Okay, so this would still work, right? But when I call distance now, so if I do this, if I run it this way, now when I call distance, I can't just say origin. I have to say, I want to know the distance from 2, 6. I'm going to run this again, right? And now it can take any coordinates. The reason we used other here is it's just a stand-in, right? It could be Z. And now I'm setting it up z.xlog. So what's going on here? What I'm saying with this is, I'm going to use this to calculate my distance from other coordinates, and other coordinates are going to have an xlog and a ylog attribute. And so that's why I'm using this parallel structure here. So now when I do that, I run this again, got to instantiate this thing again. And now when I do oops. Now I got to do distance from origin, because that's this coordinate. Origin has an xlog and a ylog characteristic. And now I'm calculating distance from that. Did that make sense? Okay. We're going to do a couple more examples, and that hopefully make it a little more clear. So we've been using print statements a lot, right? If I do print, this is what we get. All this is saying is that there's an object stored in the memory over here. So all of a sudden, print statements become less useful to us. So to make print statements more useful to us, we need to define a method called string. So let's go back up here and update and add another method. And we just have self because we don't need any other information. And we're going to print. Oops. So I'm going to run this guy and this guy. I have to run this again because every time I update what the class is, if I want to use those new attributes, I need to re-instantiate the objects. And now what's going on? This is not behaving the way I'm expecting. This may be something that has changed. Oh, I got to return this. Yeah, no, it's my fault. I need to return it and not just call the print statement. Okay. You got to run this again. Sorry about that. So when you can set up in your object a dunder string method with a return statement, and then whenever you print coordinate, I'm not sure what's going on. I don't think it matters that much. We will figure out what I'm doing wrong and update that. But let's move on. Oh, it's lowercase instance, sorry. Okay, so this is worth examining here. So I got it working, but now it says can only concatenate strings, not integers. Self.xloc is an integer. So I have to convert that or cast that to a string to be able to get this to work. So a lot of little things can go wrong, but if you don't panic, I didn't I've got to instantiate the instance again. There, finally. Sorry about that. So I had to convert it to a string. I had to instantiate object with the new definition, and then I could print from the string, and that makes it a little bit easier to keep track of where everything is. Right. So here are some things that might help when you're working with strings and objects. You can print type, origin. You can print type and it says main coordinate. You can print origin, you can print coordinate itself, and it says class. So it says the same thing, right? Origin is of type, is an object. The type for origin is of class, and it's user defined in main as coordinate. And if you print coordinate, you get the same thing. You can also do is instance to check if the coordinate is an instance that you expect. Is instance all right, what are my errors here? 1, 2, 3. I've got matching. This is not anything. Yeah, so true, right? It tells you that origin is an object of type coordinate, is an instance of type coordinate. You can set up other methods. If you want other special built-in methods, you can do add, subtract, equal, less than, length, string. You can set up all of those with dunder inits to make them work directly too. Those are some ideas for what you might want to do for coordinates. Sorry, do for objects. But in general, in CompuCell, we have a whole drop-down menu of different methods that you can add to a class, like secreting a certain cytokine and calculating how fast that cytokine gets secreted and what pattern it disperses in, and things like that. So the power of object-oriented programming. Well, okay, let's do this example. In the next couple minutes, so at 4:38, let's do it. Let's go to a 4:42 on this. Create a new class.
I think
to
there's a
represent two
question.
numbers.
Is there a question?
What is it?
Yeah, I was just wondering, so for printing, why did we define a function which converts it to string? Is this because that's how print works? Or why did we not just define a method for that class named print itself, something like that?
So it's because print is a built-in in Python. So if you want to overwrite it, you have to have a string like that. But you could it would have been, you could define, right? I could do this, print data or something that's not a so notice the color change.
Right.
It's light green right there. That's preset. You don't want to mess with that. But
Okay.
instead you could do print XY info or something like that. And then
So do Python allow us to change the inbuilt print function?
The function, no, but these dunder inits can be. So
Okay.
these methods, there is information associated with string, and you can overwrite that. So that's what that list was here. These are ones that it suggests that you can do stuff with.
Right, but we cannot modify the print function for this class. Like the by default inbuilt print function. We cannot override that.
Yeah, I don't know. No, you can't. You to do that. I mean, it's possible, but not simply by doing this.
Right. Okay. Thanks.
Yeah. So yeah, the easy thing here would have been to do print self dot xlog comma self dot ylog. Right, and then it prints out like that.
Yep. Got it. Thanks.
Okay, so no, I think this is not necessary. I think we can skip this. Because this is the same as before. It's just adding in the, well, okay, let's go ahead and do it then. Go ahead and update coordinates. So we already are able to do this. We're already able to calculate distance to another instance. I've already shown you how to calculate relative coordinate. Okay, so basically what we're asking you to do is add a method for, so we've shown how to calculate distance. Add a method for calculating the relative coordinates with respect to another instance. We already have the print representation. So it's 441. Let's go to 444. Come up with another method for calculating the relative coordinates. So if something is if you have one instance at 2, 2 and another instance at 4, 7, then the relative coordinates for that second instance would be 2, 5, right? Because it's the distance between that and whatever you input. So let's create another method that will calculate relative coordinates with respect to another instance. Okay, let's see how you guys are with this more. Let's do polls. Okay, there's a poll. You can tell me where your guys are at. Okay. Well, it looks like we're losing a little bit of participation in the exercises, which I don't blame you. I know it's been a really long day for a Sunday. But if you will just pay attention, I think by the end of this, you'll see kind of how you can do interesting things in Python, and hopefully it'll be motivating for the rest of the week. So here's how I would do this. Define relative rel chords. And then since it's relative coordinates, you need self, but you also need some outside input, right? And then rel chords x is going to be self dot x loc minus outside input dot x loc. Right? So we specify it has to be to another instance. So we know that thing's going to have this characteristic. And then we can copy this over. And then we can return if we wanted to get really fancy, we could add add attributes for rel coords X and Y, and then use these to update that, but we're not going to do that because I don't think that's necessary right now. So let's see how this works. Shift enter. Okay. Let's do inst1 equals coordinate 1351, inst2 equals coordinate 711, and then we will do print inst1 dot rel coords, and the input has to be inst2 so it goes 6 and 40. But what if this was 11 and this was 31? You get a negative number there, right? If you didn't want the relative you didn't want a negative number ever for this, you could do absolute value around that. And that's just ABS in parentheses. Oops. And that would have given the absolute value. Okay. Sarana asked, what's the utility of relative coordinates versus exact? There's not real. I mean, it's just an example of something you could calculate. Like I suppose, I mean, distance. Okay, so I guess one way to think about it is this distance is giving you a XY distance, right? It's going to give you a linear distance, 5.7 or whatever. Whereas this might give you the X distance and the Y distance if there's something that's moving only in one dimension in your system because you have a 2D system. So I mean that's kind of an unusual case, but that's somewhere where it could come in handy or something like that. But this is more just to kind of illustrate some simple arithmetic to illustrate stuff. And then Darshan, can we return another coordinate instead of the X and Y values? I'm not sure what you have a suggestion or. I mean, we could return anything. Like we could just say return 7 no matter what. Like one thing you could do for methods is if X is less than 5, move to X plus 5 or something like that, based on like maybe like a zone of inhibition or something like that that the cells have to move out of or something. I think the things I want to show you at the end. Okay, so Darshan raised a good point. These are supposed to be floats, and I returned integers. The way to address that would be float. So that's what I should have done there. And if you didn't want to float, if you wanted int, you could do this. And theoretically, you could also deal with it qualitatively. You could set up a conditional to where if either of those is between if either the relative coordinates in the x dimension or the relative coordinates in the y dimension are less than 10, you can say it's close. But if either is more than 10, you could say it's far. You could have something like that for characterizing the distance between two things in both dimensions. This example is a little bit limited. I mean, although cells do have XY coordinates themselves don't have many other properties that we can work with. I do want to show you at the end some somewhat intuitive and interesting, well, I think are interesting examples of just what we've learned so far. If you're good there, I want to move on and show you some of the other built-ins in Python that will help. And then I'll try to show some of the examples that I think are intuitive. So the point of object-oriented programming is to bundle together objects that share common attributes and procedures that operate on those attributes. And you can use abstraction to make a distinction between how to implement an object versus how to use the object. So what I'm saying is you have to simplify things to get them in your system, right? A real cell is an incredibly complex thing, and you have to distill it into a small set of attributes, the minimum number of attributes that you can actually plug into your system. And then you have to, that's what it takes to implement it into your model. And then when you use that thing in your model, then you can try to make inferences around that. You build layers of abstraction that inherit behaviors from other classes of objects. So I've always used the example of cells, right? But actually, when you're doing virtual tissue modeling, you might have the relevant operating unit may not be cells. That might be tissue, or it might be substrata, or maybe a layer of cells or something like that. And then the layer of cells is going to act based on how the individual cells in there act, or the individual cells in there act. The individual cells might react based on how the elements of the actin cytoskeleton act, or depends on what are the relevant units for your own system. And that's kind of the art of this. And that's, again, why I'd say, like, if you have to miss a day of the workshop, I would miss a day of the workshop and I would make it to the hackathon. Because that's when you really get some experience in trying to figure out, like, how do I get my model, my incredibly complex real world model into this digital thing in Python in a few hundred lines of code. So we got to do, there's some stuff we need. I've referenced this a little bit before, that there's these libraries that you can import into Python, and we use them to generate reproducible randomness. So there's a library called random in Python for generating random numbers, but they're not actually random numbers. Nothing on a computer is actually random. It generates pseudo random numbers according to certain distributions. And if you select a random seed, that seed will always generate random numbers in the same order. And that way you can see whether your simulation responds the same way. So that way, when you run your simulation twice, you know if it responded differently due to some random numbers, or if it responded differently based on some changes you made, or something like that. So these are some commands for using that library. Let's just work through it real quick. Whenever you have a library, you have to import it. Import random. So I've imported it, and now I can do random.seed35. So if I do random.seed35, random.random, which returns a random number, is going to be 0.548, and I do random.random going to be 0.75, 0.747, okay? Now, if I run this again, run, it's the exact same numbers, right? But if I do a different seed, random seed 34, it's a whole different set of random numbers. Now the 50, whatever it was, is now 52 or 0.528. And now this is 0.585. And now this is 0.843. Whenever I do random seed 34 on my computer and on yours, well, I have to reinitialize it. Yep. And then the first random number is going to be that 0.528. And that way we can get the same simulation to run on my computer and on yours. And then you can specify random.uniform from 4 to 10. So the first 3 times I do it, it's going to be 9.3, 9.2, 6.18. And I can do random integer. For 7. You can do random choice within a sequence. So if you have a list of numbers, you can do a random choice within those numbers. And then you can do a random Gaussian distribution, meaning a random number with mean mu and a standard deviation of sigma. So if I do random.gauss, mean of 5.5 and a sigma of 0.4, I get 5.8 one time, I get 5.4 one time, 4.8 one time, 5.1 one time, right? It's gonna give those numbers in this distribution. Any questions about that? The next library that we need to know about is time, and it provides functions related to time. And it's based on the beginning of time according to your machine. So if I do import time, time.gm time 0, time.time, time.sleep 2, print, so hold on, watch this. Print A, time.sleep 3, print B. Okay. Right? It waited 3 seconds. That's what sleep does. It waited 3 seconds between A and B. You might do that if you need to, if you want to watch and see what happens in between certain points in a simulation. Time.time is, yeah, how long since the beginning of your system, or not system, the server in this case. And then, yeah, so GM time is January 1st, 1970, whatever. So it's going to be time.time is going to give you the time since that 1970 date, and that can be converted. Oftentimes you do is what, see that's 1659, blah, blah, blah. Time.time. See, this changed about 10 seconds apart, or not even 10 seconds, wait, some number of seconds. But anyway, what you can do is okay, C is time.time, D equals time.time, and then D minus C, 9 seconds between them, right? And so that way you can time how long your simulation is taking, because it's the difference between when we recorded time here and when we recorded time there. So that's also useful. Any questions about any of these so far? Another useful one is math. I'm not going to do all of these because these are kind of obvious. Import math. Math.py is, well, you guessed it, it's pi. Math.infinity and math.nan are also values that you can use in a distribution. Math.ceiling, so watch this. That rounds up to 4, right? Math.ceiling, which means round up, and then we take pi in there, and then math.floor. That's a 3. ERF is an error function. So that's going to keep track of how far away something is from some ground truth. Exponent's going to raise it to exponential, and then log is going to take the log of something. Factorial is, as the name suggests, going to take the factorial of something. So obviously this needs to be an integer here. So factorial 6 is going to be 6 times 5, 4 times 3 times 2 times 1. Square root is going to be the square root of it. And then these are trigonometric functions, which can be useful for figuring out various angles for branching events and things like that. Any questions right now? There's another library, statistics, which is going to calculate mean, median, quantiles, and standard deviation. So you can use that to calculate some results on your simulation, or to generate some values to use in your simulation. So let's do this one together. Actually, let's come back to this. I want to show you an intuitive simulation first, and then I'll come back to this one. So this is not necessarily a biological phenomenon. This is more of a social phenomenon, but the point is to illustrate how you can how you can use the concepts that we have learned so far to generate a complex coordinated behavior, to map a complex coordinated behavior. So I want you to think of a standing ovation. So in a standing ovation, generally people are clapping, and then one person stands, and then more people stand, and then more people stand, right? It's like a social contagion. If you were modeling a standing ovation, imagine that this is our audience in a standing ovation. We could make a user-defined class for each member of this audience, right? We could have their XY position, so we can tell which members of the audience are neighbors of other members of the audience. And then we could iterate through the audience members and figure out, one, how stimulated they are based on whatever they saw. That would give a certain arousal level. And then the other factor in the standing ovation is, are other people around you standing? So they could all have their own individual arousal level based off of whatever stimulus that they're responding to. And then they could do a form of quorum sensing, right? They could tell, like, oh, half of the people around me started to stand, so I might stand, or 3/4 of people around me started to stand. That's making me more likely to stand. And so you can iterate through that, and then you'd have to have a decay function because standing ovations don't last forever, right? After a certain amount of time, they lose steam and people feel like, okay, I've clapped enough. And then they start to descend down there. Then the arousal level descends until a point where they don't, where they stop standing. So you can actually model this, and this was published in the 90s by somebody. So this is very similar to, or this is using just things that we've done before, right? Class, audience member. We use a constructor, use X location, Y location, and then we keep the attributes of status for whether how excited they are, and then tendency, how likely they are to stand. And then we have to do something called peer pressure, right? Because it's going to depend on how stimulated other members of the audience are that will help influence how much they stand. So what you can then do is create a list for audience, and inside that list, you can create for X in range 30, you can create an object, an instance of that object with an X location of X, a Y location of 0, an excitement of 0, and a standing tendency of 1.1. And then you append that object to the list. So now you have a list of 30 audience members, each with a different X location, 1 to 30, or 0 to 29, actually. And then all with the same Y location and all with the same excitement and standing tendency. And if you'll forgive me, I have a little black box here. It's going to map the audience, and it's going to say for the audience, it's going to say if they have a if most of the audience is not standing, or if they're standing, they're going to be black. If they're not, if they're if they're clapping, it's going to be black. This is less than, sorry. If they're not clapping, they're going to be black. If they are clapping, it's going to be blue. And if they're standing, it's going to be red. And so we can just instantiate that, and then we can map our audience so far, and we just have a bunch of black dots, right? Because they're not clapping yet. You can do the same thing in both directions, right? You create an X and a Y, and again, not give them any excitement level. You're storing those objects inside of a list, and then you're just mapping that whole list. And so now you have a 30 by 30 grid of audience members, but they haven't had any stimulus. They're not clapping yet. Now we can go ahead and put in the peer pressure. So some of this, we didn't teach you how to read lambda functions or whatever, but the point is you create a list called peer list, and that peer list is going to select other audience members that are within 3 of their X location, and then 3 less than 3 or greater than 3 of their X location, and less than 3 and greater than 3 of their Y location. That means for every given audience member, it's going to keep track of their peers in a 9 by 9 grid centered around them. And it's going to keep track of how many of them are counting, how many of them are standing. And if some of them are, and for each one that's standing out of that 9, it's going to create a variable called stand peers, and it's going to increase their arousal by a certain amount based on how many of them are standing, and by a certain amount of over how many of everyone is standing. So the people around you are going to influence you the most, but you still get some influence from other people in the audience. And this is a decay function. After 10 calculations, after 10 seconds of this, you're going to start to decay your arousal no matter what. So we can map that, and then we can take a look at this. And this is, the audience has been mapped. So we're going to start with no one standing, but a few people, red people are standing, blue are clapping, no one is silent. So if you saw that, it started to spread. It started, so we can run it again. Oh, I didn't reset. Hold on. I need to reinitialize the audience, recreate the objects. Okay, so these are the people who are standing and the rest are just clapping. And you can see it starts to spread locally, and then it passes a certain tipping point where everyone starts to stand. And this time it never reached fully standing. So this isn't a very well calibrated model because it's not based on any experimental data, but you can see, you can imagine how you can get complex coordinated behaviors off of very simple uses of classes. We're just keeping track of 3 variables: how long they've been standing, how excited they are, and their X location and Y location. So the models that you'll be making in CompuCell are more sophisticated, but they operate off of the same basic principle. And they'll be more grounded in data, so you'll get more well-calibrated systems that have that operate more realistically, and that you can ask questions too. You can ask questions about, like, how aroused does the system have to be? How important is, or what is the effect of having someone who will never clap, or people who will never clap in there? Or what is the effect of having people who clap a lot, who automatically clap a lot? You can find the equivalent biological questions for your system. What is the effect of increasing, what is the effect of lowering the threshold for activation of a certain cytokine release? What is the net effect of that on the system? So with that said, let's go ahead and do this example, this random walk example. So a 1D random walk. For each step, a particle can move either up or down 1 unit with a probability of 0.05. So you can use a coordinate, right? Go ahead and use that coordinate class to generate a coordinate, and then give it a method called random walk, in which its X direction gets updated based off of a random number with this, probability. And I'll pull up those commands on the screen. Simulate 100,000 steps and report the position, the standard deviation, and the root mean square. So to do that, you're going to need to not just have it move, but have it store that. So go ahead and store that in a list. Append the X position to a list after each step, and then run this and see how long it takes to simulate. So let's go ahead and spend 10 minutes on this. I'm going to copy these onto one screen. All right. I think that's enough to be able to let you do it. 516, let's go to 526 on this.
Can you zoom it out? I can't see the probability. Yeah, thanks.
Okay, so let's go ahead and do some of this. Okay, so we're gonna need the library random. You only have to import it once, but I just want to import it here just to emphasize that we need it. And then we're going to need to create a class. So we create a class with the keyword. Let's call it chord. Then we can set up our constructor with Thunder in it. Def double underscore in it, double underscore. First thing we have to do is enter self. What other attributes do we need to set up this random coordinate? We just need to know its X location. It's a one-dimensional random walk. So we can get self.xloc equals X, just as before. The other thing that we're going to need, if we want to do stats on everywhere this thing has been, we're going to need to keep track of its location. So let's create self.xhist equals empty list, with xhist being its history. And then let's create a method. Def rand walk. Do we need any input arguments for rand walk? Well, we always need self. Do we need any other input arguments? And the answer is no, right? Because we don't need to know anything about the outside world to run this. We just need to know where this thing is in order to have decided tell it to move. Okay. Now remember, our prompt said, give it a probability of moving either up or down 1 unit with a probability of 0.05. So I interpreted that as a 0.025 chance it moves up and a 0.025 chance it moves down. The easiest way to do that is generate a random number. Z equals random.random. Now, what does random.random look like? Let's just remind ourselves. Just experiment here. Oh, okay. It looks like a number between 0 and 1, right? Well, if a number is between 0 and 1, there is a 0.25% chance that it's going to be greater than 0.975, right? 2.5% chance of being greater than that. If it is greater than that, I want to move it up. Plus equals 1, right? In other words, self equals self.xloc plus 1. Elif, if it's not greater than 0.975, let's just say if it's less than 0.025, so it's a 2.5% chance of being less than 0.025. Oops, got my quotation mark in the wrong spot here. Here we go. Self.xloc equals self.xloc minus 1, right? If it is a 2.5% chance of going down 1, and it has a 2.5% chance of going up 1. Regardless of what the random number is, let's go ahead and add it to our memory. so we can append it to our empty list. Self.xhist, our x history, which is a list, dot append, and let's go ahead and append self.xloc. Append our new x location. And that's it for the coordinate. And now that we have that coordinate, let's create an object. We'll call it point one. Well, let's call it random walker equals chord. Let's start them at 0. Okay, let's check his x location. His x location is 0. Okay, so then let's do 100,000 steps. I'm not going to do 100,000 steps just yet. I'm just going to do 1,000 steps because I don't know how long it's going to take computationally. I'm just going to keep it simple. For range 1,000. Right? Remember what range does? It sets a number from 0 to 1,000. Random walker dot rand walk. So each time x is incrementing between 0 and 1,000, we're going to run this random walk method, right? We're going to generate a random number. We're going to test if that random number is high enough to move up 1 or low enough to move -1, and we're going to append it to our history. So let's run this guy. It ran fast. Okay. How do we know if this ran? Well, no matter what happens, our random walker should have a history of where he's been. So let's check the length of random walker xhist. It's 1,000 steps. Okay, let's check the min of it. He should have moved off of 0 at least once. Yeah, he gets as low as -3, and he should move above it at least once. It got as high as 16. Wow. Well, let's find the mean of that. So we can import statistics. Statistics dot mean random walker dot xhist. His mean position was 5.223. We can find out the standard deviation. Statistics has no attribute standard deviation. Okay, so now I got to Google Python library statistics standard deviation. Literally Google, oh, it looks like it's STDEV. So here's the documentation. This will show you what they are. STDEV. So I'll go back to here and change this to STDEV. That's the standard deviation. And then what else did it ask for? Position mean, standard deviation, and root mean square. Well, how do I calculate root mean square? Do a quick search. Let's sometimes Google search is better. So you need actual versus a predicted to generate this. And then you can copy this over. I just copy this code over. Okay, so and then I need to generate a predicted for this for this guy. So my predicted is going to be a mean of 0 and probably the same standard deviation. And then I could run this and get the root mean square error. But anyway, now let's just do this again for that 100,000 that we talked about. Because I don't actually care about the root mean square, but I do want you to know. So I'm going to run this guy again, random walker. I set him up with the coordinate 0. So it's coordinate 0 again. Now I'm running it for 100,000 units. It, again, ran pretty fast. I'm gonna check the minimum on the X history is -14. Max on the X history is 167. The mean is 93 here. Standard deviation is 50 after 100,000 runs. So, I wonder if there is some bias in the way I set up my method, but if not, this is basically how it works. Right, this time it was negative bias, okay. Yeah, so these change a lot, which means that we're not close to where we need to be to get a model that's starting to, okay, so that was too many. Let's get one less 0 in there. Okay, so that took a while to run, but it still ran. Okay, anyway, any questions about this so far? Did anyone do it a different way?
Is there any specific benefit of using classes here? You can just like generate the random number and keep incrementing it even and doing it on a list directly, and then
Yeah.
basically
So at this
doing
level of complexity, there's no benefit. But if you have a bunch of these, right? If instead of coordinates, they're cells, maybe they're bacteria or protists,
Yeah.
something that moves.
Yeah, then I
around
can
a lot.
imagine, right?
And then and then that's where the benefit actually comes in.
Right. Thanks.
Let me see. Well, if we have a few minutes, I want to show. Any other questions?
I just wonder if you adopt some code from Google, like what you found at Google Story there, and it's not in your, it's not recognized. Part of it may be not recognized by the Python that you build or have working. What do you do? How do
The
you tell the
key-
Python to recognize something that is not prepared ahead of time?
So if you put in Python code from the internet, it should recognize it. The main issue will come so like this one that I copied in here needed NumPy, right?
Yes.
And I didn't import NumPy yet. So then that could have created an issue. So sometimes there's dependencies. Sometimes there's dependencies that are not available, but other than that, it should be able to work. Sometimes there's variable names
Those
that aren't. So if I
dependencies,
do
you have to take care of those dependencies every time.
Yeah, with importing. So if I do this right now, right, I've copied this in. This isn't going to work. And we'll see what the errors are. So one, NP is not defined. I never imported NumPy. So if I do that, there'll still be some problems. And then the next thing, Y actual is not defined, right? So that's often what the issue is. So if I make up some Y actual, I'm going to make up some Y predicted. Oops. Commas. Then I run it. Then I was able to come up with something. So oftentimes, as long as you just have to step through and make sure you've defined everything. And so realistically, I haven't adapted this to my problem. I need to change Y actual to random walker X hist, and I need to come up with some Y predicted in order to use this this code. So that's probably the key there is checking on libraries and checking on dependencies. Sorry, libraries, and then checking to see if all the variables that they're using have equivalents in your variable space. Any other questions from anybody? Well, if there's no questions, I might show another example that I use in one of my classes that's not explicitly a biological scenario, but maybe is easy to interpret. Okay, so I have a class called agent new. Has an X location and a Y location, as we've talked about before. It has a status. The status is starts out as unhappy. And then it has a group. It can be either a purple or a yellow. And then it has a method called move if unhappy. So as long as status is unhappy, it's going to move to a random new location. And then it's going to have a method called check neighbors. It's going to check every neighbor within 100, within a 10 square grid radius of itself. And if most of those neighbors are in the same group as it will decide it's happy. And as long as it's not in the minority, right? As long as it's not a purple agent that's surrounded by more yellows than purples, it will be happy. As long as it's not a minority, it will be happy. And then we generate a bunch of these, generate 100 by 100 grid of these. And we have them move, and you can see very quickly they segregate because not one of them wants to be in a minority situation. So it moves until it ends up in a stable equilibrium, which is unhappy. So in the 1970s, when people were doing the first simulations of social phenomenon, they interpreted this to mean that there's very minimal preference needed to cause this segregation. You don't have to be extremely hostile to other groups. You just have to have a slight preference for the same group. But if we update this module, if we update our agents and add some called diversity seekers, which are happy when they are in the minority, and then we run the same simulation, but with a few of those things, it never gets as segregated because some of them like to be in the minority and it keeps it more coalesced. If you think of this in terms of cells, so this suggests that the present, like a heterogeneous set of characteristics leads to more mixed outcomes, right? And then, so if you think of this in biological context, you have this type of sorting all the time during differentiation and stuff, where cells with similar characteristics need to join with each other, and obviously they don't move randomly; they're going to move incrementally. So it's not exactly the same, but you can find kind of complex simulations. You can find kind of complex simulations at you can get complex behaviors to emerge off of very simple simulations, and finding what are the thresholds that matter for that. Qualitatively, do you need a big input for stimulus X, or is a small input for stimulus X sufficient to create the phenomenon that you're looking for? That's really how you interpret these models. It's easy to hard code something and make it show up every time, but part of it is figuring out how to ask the question in a way that's analogous to the questions you ask in lab. Is protein X necessary for this phenomenon? Is it sufficient for this phenomenon? You get trying to set up your model so you can ask the exact same questions in the system as you would in an experiment is the whole goal of CompuCell3D. And the beauty of CompuCell3D is, unlike your actual experiment, it makes you state your assumptions. So the assumption in the old model there was that every one of these agents had homogeneous interests. But if we introduce some slight variations in how the agents behave, you get completely different phenomenon. And that makes it seem that the rules that were identified earlier are less robust than we thought. So they're going to teach you about how to do that during your simulation. I encourage you not to focus on how to code the simulations, the demos that you get shown. Don't focus as much about the coding. Focus on how they represented biological realities. What phenomenon did that? What characteristics of the model did they ignore? Did they black box? Or did they hard code? And what characteristics of the model did they carefully simulate?